In this video, I'm going to be discussing some of the basics about waves. Take a moment and read the success criteria for this video. In this video, I'm going to be talking about mechanical waves. That is, the ones that need a medium or something they have to travel through. They could be traveling through water, air, basically anything except for going through a vacuum. One of the things that's important is what they're transmitting is actually energy. It's not the particles themselves. An example I like to use in class is the fact that when you talk to someone, their hair doesn't go whoosh back because the air is going from your mouth to their face. It's actually just one particle hitting the next, and transmitting energy till eventually it gets to your ear, and that's what you hear. My diagram here has two different types of waves, both transverse and longitudinal. You can see in this case that I have the vibration of the particles going in different directions. In this case right here, we call them longitudinal, and that's because the vibrations of the particle go in the same direction that the wave's going to travel. Whereas down here in transverse, the particles actually go up and down, but the wave is moving in this direction. An example of a longitudinal wave would be sound. Transverse waves would be like water waves, or you can get both of these types of waves happening in a slinky. First, we're going to go through some vocabulary. Some pieces of the transverse wave. Here at the top, we call it a peak or crest, and down here is a trough. Now, I know English is an ugly language, and you look at this and say, how do I say it? I always remember it's trough, cough. Down in our longitudinal waves, when the springs or the particles come closer together, we call it a compression, and when they're farther apart, we call it a rarefaction. This line right here, I call the equilibrium line. That's where all my particles would be if there was no wave transmitting through the medium. If I look at here now from the equilibrium line to the top of the peak, that will be my amplitude. It is a common misconception for students to think that it goes from the peak down to the trough, but in fact, it's only halfway there. Also, all of our waves will have the amplitude being the same distance from the equilibrium line to the top or from the equilibrium line down to the bottom of the trough. Likewise, in a longitudinal wave, we can talk about how far it is from its equilibrium to where it's been displaced. This is a lot more difficult to see in a diagram like this, but I have one coming up later that will talk about how we can measure this and see this in a longitudinal wave. Okay, so let's talk about wavelength. You can see there I have a definition. It's the distance between 2 points in phase. Now, what do I mean by in phase? Well, they're going to have the same displacement from the equilibrium. So, for example, if I choose this point right here, my displacement is this length right here, and they're going to be going in the same direction. So if I chose this point, the next point that has a displacement of that same amount would be right here. But that is not going to be in phase, because whereas the first one's about to move up, the second one's about to move down. So let's get rid of that one. If I want the next point in phase, I'm actually going to need to go all the way through and back to here. Now, those 2 points are in phase. A lot of the time, some people will say from just one peak to the next, or one trough to the next, and you have to say the next one, not just any one. But if you look at all of these distances I'm just drawing here, they're all exactly the same. So that is our wavelength. The letter for wavelength is lambda, and how you draw that is like this little curve and then a stick to prop it up. Likewise, I can do the same thing on my longitudinal wave. I can go from one center of compression to the next, or I could do it from the center of a rarefaction to the center of a rarefaction. Again, notice those two lengths are exactly the same size. That is a wavelength. I have two more things I want to talk about. First of all is the frequency, and the other is a period. So let's take a look. Frequency is the number of cycles per second. Now I've written the cycles there because it's a little shorter, and typically we'll use the word oscillations, just like we do in simple harmonic motion. So let's see. If I do 5 oscillations in 1 second, then I would call that 5 hertz. Now, if I can do 5 of them in 1 second, then that means each one of them took 0.2 seconds. And you can see here from this equation that I can find in my data booklet that the period, capital T, and the frequency are inverses of each other. The only last thing I have on this slide here is this equation C equals F lambda. C stands for the wave speed equals the frequency times the wavelength. Now the frequency is the number of cycles per second times the wavelength, which is the distance that wave travels. So this is actually just the same as saying distance divided by time. That is a wave speed. So remember I said in this Slinky we can actually get both a transverse wave and a longitudinal wave to occur. So if I was going to create it with my hand and I was going to make a longitudinal wave, I'm going to move it back and forth. A transverse wave moves up and down. Now, one of the things I get my students to do in my class is I get them to put a little piece of masking tape all the way through their Slinky so they can actually watch what happens to these pieces depending on what kind of wave I have. And what you find is that that piece of tape never makes it all the way to the end. It kind of supports this idea that only energy is being transmitted and not the particles. Those little pieces of tape are just going to move in the same direction that the hand is moving. Now here's another really key point. I have a wave speed. That is how fast can this particle transfer it to this one, transfer it to this one, and that will be indicative of my wave speed as I marked here. But if we talk about the particle, or example, my little piece of masking tape here, what does this particle do? Well, it's going to move forwards and backwards. What does that mean? It's going to have to go forward, speed up, slow down, and stop. Change direction, speed up, slow down, and stop. That means my particle is actually undergoing simple harmonic motion. Likewise with this particle, it's going to go up to the peak here, and then it's going to change directions. It'll speed up, and when it gets to the equilibrium line, it's going to slow down, stop. Change direction, speed up, slow down, stop. So it also will undergo simple harmonic motion in this direction. So our wave speed is constant, but our particles are undergoing simple harmonic motion. So let's bring all of this information together with a few practice questions. At the top, I've got spring X. It's being moved side to side in this direction. You can see we've marked the direction of wave travel. In spring Y, backwards and forward motion, and again, the direction of wave travel. How should the wave motions in X and Y be described? Take a moment and read through. Okay, so the top one is going to be transverse. So spring X is transverse. Here's a technique to answer these kind of questions. Scratch off the ones that are not correct. In our second column, spring Y, we know that's longitudinal. Again, scratch off the ones that are wrong, and we can see that the answer has to be C. Take a look at this diagram. First, can you tell me what is the amplitude? That's letter A. And what about the wavelength? That would be C. Now, one thing to point out, if we say that C is our wavelength, that assumes that we have displacement versus distance here. That would be like a snapshot of the wave from the side. In that case, C would be, according to my x-axis, giving me something in meters or some distance. If I change this, though, and now I have time here, then actually C would give me the period. For more on this, you can watch my other video that talks about motion graphs for waves. So which of the following best describes the speed of a water wave? Now I hope you realize A says the distance. B says the distance. It can't be either of those two. Now C and D are a little different because they say the distance that it moves in 1 second, or the distance a wavefront moves in 1 second. So those are going to give me a speed. Let's look at them a little bit more carefully. In C, it talks about the distance a particle of water moves. And in D, it's talking about the wavefront. So our particle, remember, is undergoing simple harmonic motion. And the wave front would be like watching the crest of the water wave move along the surface. So our answer is D. So what is the number of wavefronts per second that pass a fixed point? So let's think about it this way. I've got a whole bunch of waves, and I can either think about how fast I make them, or if they are moving by me and I'm a person standing right here, how many pass by me each second? Both of those are telling me about the frequency of the wave, not the speed, because that would be a distance per time, not amplitude, that would again be a distance value, and wavelength is also a distance value. This is another way to think of the frequency of a wave. How many of them pass by a fixed point per second? So here's a diagram about a wave. Remember, anytime you have a graph, look very carefully at the axes. How many wavelengths are there between x and y? Start here. 1.5. And our last question. Astronaut number 1 uses a hammer to mend a satellite in space. Astronaut number 2 is nearby over here. There is no air in space. So, compared to the sound they would hear if they were on Earth, how do you compare the sound that astronaut 2 hears? No sound at all. Sound will not travel in space because there's no air for it. Sound's a mechanical wave. Now, these last questions should seem a little easy. They're probably a little bit easier than you would expect on an IB test on paper 1, but I do think they're good at this point to help make sure you understand some of the points of these concepts. So now at the end, please go through and reread these success criteria. I hope after watching this video, you can say yes to all of these.